Good morning, afternoon, everyone. My name is Mitesh Patel, and today I'll be presenting paper 207, which is Enhancing Indoor Localization Accuracy with Bluetooth Low Energy RSSI Signals Analysis Using Machine Learning Algorithms. This work addresses a very practical challenge. How do we accurately locate people and asset indoor where GPS simply doesn't work? So let's dive into this. Here is a quick roadmap of what I will cover today. I'll start with a brief abstract and motivation, then move into the introduction to set the context, then review relevant prior work. From there, I will walk through the research methodology, present our results, and close with conclusion and future direction. We will have time for question at the end. So I'll ask everybody to keep the question at the end. Thank you. So let's summarize the introduction. What this paper is about. Intelligent environment like hospital, warehouses, and smart building need accurate real-time indoor positioning. GPS is unavailable or unreliable indoors, so we look at to Bluetooth Low Energy, which is BLE, as a low-cost alternative. However, BLE RSSI signals are highly noisy due to multipath effects and interferences, and so our solution is a machine learning framework combining stability-focused pre-processing, strong feature engineering, and a dynamically weighted hybrid assembled approach. The key finding, tree-based models, especially XCG Boost, achieved the lowest positioning error with random forest scoring R-squared of 0.993. Importantly, stacking ensembles outperformed deep learning models like LSTM, demonstrating that ensemble learning is the right direction here. So let me set the broader context. Indoor localization has wide applications, as you know, which is smart buildings, healthcare monitoring for patients, navigation in large venues, asset tracking in logistics, and emergency responses. The challenge is that GPS, our go-to outdoor tool, fails indoor because signals are blocked by walls and floor. And so BLE has become the dominant technology for indoor positioning. It's inexpensive, energy efficient, and built into virtually every smartphone. But BLE relies on RSSI, which is the Received Signal State Indicator, which is notoriously unstable. Human movement, furniture, and even orientation of a device can cause dramatic fluctuation. Traditional approach like fingerprinting and standalone machine learning models struggle in noisy, heterogeneous environment. That's the gap this work addresses, which is a robust end-to-end machine learning framework designed specifically for those challenging conditions. Looking at prior work, I have summarized 6 key papers in this table, and you can see a clear trend. Researchers have been combining BLE-RSSI with increasingly sophisticated models. Ayub et al. In 2025 used XC-Boost and random forest with Kalman filtering, good robustness but limited large-scale validation. On the other side, Yang et al. Also in 2025 applied CNN with multi-head attention, achieving an impressive 0.29 meter average error, but with highest computation cost. W et al. Tested CNN against classical methods, finding CNN best at 1.22 meter, and then Baje used Bayesian hyperparameter optimization with XGBoost, achieving 91% accuracy, but only at room level granularity. Two other papers achieved strong RMSI value but under limited environment condition. The common gap, none of this works combine stability pre-processing, advanced feature engineering, and ensemble strategies in a unified framework, which is what we have contributed in this paper. Now let me walk through our methodology, which you can see as a flowchart here. We start with an indoor BLE RSSI dataset. After data collection, we apply rigorous pre-processing, noise removal, and signal stabilization. We then perform feature engineering to extract the most meaningful signal characteristics. To handle class imbalance in the dataset, we apply SMOTE, which is synthetic minority oversampling technique. Features are then normalized for consistency. The dataset is split into training and testing sets, and we implement a suite of regression models. Linear regression, decision tree, random forest, and SVR alongside ensemble approaches. And the model performance is evaluated using three metrics. Number one is RMSI, which is root mean square error, then MAE, which is mean absolute error, and then third one is the R squared. Each step was designed with noise robustness in mind, which is what differentiates our approach. Here are our core results. This table compared 13 different models. The top performance by R squared and R random forest at 0.993, stacking elastic net also at 0.993, and XGBoost at 0.991. But R squared alone doesn't tell the full story. When we look at mean Euclidean error, the actual spatial positioning error, XGBoost comes out of top with just 0.177 meter, followed by gradient boosting at 0.192, and random forest at 0.196. The stacking ensembles are competitive. Elastic net at 0.252, reach at 0.251, but they don't surpass the best models here. Notably, AdaBoost performs poorly with Euclidean error of 2.26, showing that not all assemble methods are equal. The takeaway, XZ would deliver the best spatial accuracy. And then final results, this cadence clause gives us an intuitive visual of model performance. On the left, figure 2 shows the voting ensembles. Predicted location closely match actual positions with a mean Euclidean error of 0.655 meter. Not bad, but there's a visible scatter. Uh, on the right, figure 3 shows our weighted hybrids ensemble. The predicted points sit much tighter around actual values. The variance is visibly reduced and the mean Euclidean error is 0.498 meter. This visual confirms what the number tells us. The weighted hybrid ensemble successfully combines learner strengths to produce more reliable location estimates. And then this slide compares our models against published benchmark from the literature. Look at the baseline models. KNN from prior work achieved R square of 0.778. LSTM gets 0.980. AdaBoost in prior work has an RMSI of 16.7, which is extremely poor. Polynomial regression is even worse at 69.16 RMSI. By contrast, our staking elastic net achieves R square of 0.993 with RMSE of just 0.369. Our staking reach and lasso also significantly outperform all baselines. Even our voting ensembles at 0.983, R squared beats LSTM, which is a deep learning model requiring for more compute. This validates that our ensemble-based machine learning approach isn't just incrementally better, it's actually substantially leap in both accuracy and efficiency. So to summarize our conclusions, machine learning significantly improves indoor localization accuracy even with highly fluctuating BLE RSSI signals. Our framework tackles multipath interference, signal attenuation, and environmental variation through a layered approach, pre-processing, feature engineering, and ensemble learning. Regression-based modeling enables fine-grained coordination prediction, not just room-level classification. And then among all models, random forest provides stable high accuracy, while XGBoost achieves the lowest positioning error. Stacking ensemble outperforms standalone machine learning and deep learning models for consistency. Looking forward, the next steps are transfer learning for new environments, lightweighting real-time models for edge deployment, multi-modal sensor fusion combining BLE with Wi-Fi and IMU, and large-scale testing across more diverse buildings. And so the full references list is shown here. We have total 18 references in total. We thanks all of this author that directly indirectly contributed to our paper here. So if you have any questions, I'm here. I'm here to help you with any questions if you have. Thank you. And so thank you for your attention. I hope this work demonstrates the potential of ensemble-based machine learning for practical indoor localization. Uh, I'm happy to take any question. Thank you so much.